All right. So on the screen today, you can see the agenda, what we're planning to do. You can also see a quick reminder on the right side of the two new equations we learned last week, the one for electric force and the one for gravitational force. There's also a reminder at the bottom that the next time we have class, you need to have worksheet number 3 done. And the goal today is to actually go through number 1 together. So if you've had some questions, you'll at least get some of them answered, because once you understand number 1, that should help you quite a bit with 2, 3, 5, and 6. And hopefully you have number 7 done already, since we went over that one last week. But you don't need to do number 4 or number 8. And there's a reminder of this in the description on Access, that which questions you have to do. But it's 1, 2, 3, 5, 6, 7. So, yeah, Lexi? I'll probably collect it on Wednesday. Yeah. So that's the goal for worksheet 3, is hopefully, like I said, get through number 1 together today and then collect it as a homework assignment on Wednesday. The lab today, we're going to see, you can see on the agenda, we're going to do whiteboard presentations. And when you do the presentation, just so that those that do watch the video can see, if you'll come up over here, kind of in this corner, and stand kind of like this, then the class can see it. I know it'll be a little bit hard for the back of the class, but it shows up pretty well on the camera if you kind of angle it this way. It's close enough. And once you start talking, it'll zoom in and find you. So when you give your presentations, we kind of just give them from here instead of normally we do it over there. That's really far from the camera though. And in your presentations, you'll be just drawing the graph of your data and then interpreting it. And I do need to mention that if you downloaded the rubric, or if you look at the rubric on Access, it has the corrected form. But I had already printed it before I realized I forgot to add area under the curve on the rubric. So on the rubric it says, analyze it. If you picked up the print one, I'll go ahead and put them back out in case people still need it. And down here it says, interpret the model slope and intercept. But I would like you to also include area under the curve. So if you look at it online, it says that, but if you look at the paper version, I forgot to add area under the curve in there. So make sure you do include area under the curve, both for your interpretation today and also in your lab report. And the lab reports will be due Friday. So I'll collect your homework on Wednesday, the next time we meet, and then I'll collect your lab reports on Friday, the time after that. Okay? I don't think there's any other reminders or details I need to mention other than that. Do you guys have any questions for me about the assignments or timelines? All right. So on your presentations, everybody understand what to include in your whiteboard presentations? All right, pretty brief today, just the graph and the interpretation of those graph elements, the 3 graph elements. I'll give you about 10 minutes, get with your partners, get your graphs made, get your whiteboards ready, and then we'll have presentations in about 10 minutes.
Yeah, can you send me the picture of the graph?
Exactly. So he wants to explain what.
How is that better? Gross and I.
All right, so let's go ahead and start getting these presentations lined up. Bring this group in from outside. You guys ready to come in?
He already
Wait, is kilograms squared meters?
That's the question.
Yes, that has a kilogram squared. That's not in the right spot. I don't know.
feel like it might be something. I don't know.
I can explain like the wires. I can explain.
Wait, what are you doing?
Then we just do the graph and then.
Yep.
Okay.
mathematical model.
You wait your curve.
Right.
Can you do
Graph is
Either
what
way.
you said later.
Equation weight per kilogram. Wait, should we just do meters per second?
All right, so, we're gonna have this group start, and then we'll just go here, and then there, just kind of work our way back. Again, on your presentations, come over to this corner, hold the board up so the class can see it, but also it's pretty close to the camera. I'll open this up again so you can kind of see in the little thumbnail at least if it's pointing towards you. Yeah, tell us what you discovered, so take it away. Make sure it's angled towards the camera son as well.
So our graph is linear, and it was weight versus mass, and weight equals 9.726 meters per second squared. Squared
4 newtons per
newtons.
kilogram.
Yeah.
And then the area under the curve is kilograms times newtons, which we didn't think there was an interpretation for it. So we didn't think it like.
The y-intercept would be the starting weight, which is, when we put when the mass is 0, the starting weight would be 0 newtons. And then the slope, we thought the interpretation of the slope was the acceleration due to gravity, because it's very close to 9.81 meters per second squared.
Good. Any questions for this group? Okay, very good, nicely done. Give some snaps, and then we'll go on to that group.
I have to go over here. So to start, it is a straight line. Our axes aren't entirely straight, which makes it look a bit wonky, but so our equation was that weight equals 9.87 newtons per kilogram times the mass plus or minus 0.04 kilograms. So the slope is the gravity, because newtons divided by kilograms is meters per second squared, and we got something close to what we know what the gravity on Earth is, which is 9.81, and we have 9.87. And the y-intercept should be 0, but due to just error, it ended up being close to 0, but not quite. And then the area under the curve it's kilograms times newtons, and I'm not sure if that interprets anything.
Nothing that you're aware of.
Yeah.
Okay. Very good. Any questions for this group? Let's give them some snaps. Good job, and we'll move on here to the next row.
So for our graph, it was mass versus weight, and it has a linear shape, and the slope is about 9.73 newton kilograms, with a low y-intercept of 0.02.
Okay, so our slope, it was fairly close to the acceleration due to gravity, which is 9.8. And our y-intercept, it should be 0, but we got 0.02, which is fairly close to 0 if there was no error, but there was. And our area under the curve, we don't know if it has a meaning or not. And our mathematical model is weight equals 9.73 newtons over kilograms times mass plus 0.02.
All right, good. Any questions for this group? Okay, nicely done. Good job. And let's go here to this group here on the third row. Yeah, you can go ahead.
Okay. Our graph was linear.
And it had a y-intercept of 0, which wasn't like exactly what the regression put in, but we knew that when there would be 0 mass, there would be 0 force, because the equation for force is mass times acceleration, of course. Yeah.
And our slope was 9.843 meters per second squared, which is just the acceleration due to gravity.
That caused the equation to be force equals 9.843 meters per second squared times mass. Like you said, it's like acceleration due to gravity.
And then we found the area under the curve to be insignificant.
Because its units were kilogram newtons.
Very good, nicely done. And let's go to this group right here, the other group on row 3. You guys said it was 9.83?
9.843.
What? Yeah. Are you looking for the units? Yeah, I already looked.
So when we graphed our data, we found that there was a linear relationship between force and mass. And for our equation, we got force equals 9.86 newtons per kilogram times mass.
So because our slope was 9.86 newtons per kilogram, we know that's pretty much almost the same as what gravity is. We said the slope was gravity. And then our y-intercept was negative 0.02, which is pretty much just 0. So we said when there's 0 mass, there's 0 force. And we said the equation for the area under the curve was 1/2 newtons times kilograms. We weren't sure what it was.
Good, I like that you included an equation on how you would find it. And I saw your group and a couple other groups just doing a little research, trying to check Google or Siri or somebody to see if you could figure out if that had any meaning, and so far no one has, so nicely done. And we've got one group left.
Our graph is a linear graph, and we got an equation of weight equals to 9.83 newtons per kilogram times mass plus a 0.03 newtons, and our area under the curve in units of newtons per kilogram. I forgot to put the equation on it, so same units.
And then for the slope comes out as acceleration, since it would be newtons divided by kilograms, since it's rise over run. And then this would give you acceleration similar to F equals ma, and since you just divide the mass, the force by the mass, you will be left with the acceleration. And so since it's also very similar to 9.8, we realized the slope is the acceleration due to gravity. And then for the y-intercept represents the force acting on the object with 0 weight. And since force equals mass times acceleration, if it has a 0 mass, anything times 0 is also 0, so there is 0 force acting on the object.
Very good. Any questions for this group? All right, nicely done. All the groups. Okay, go ahead and wipe down your whiteboards and you can put those away. We got some pretty consistent results. We'll discuss that here in just a second.
I can put it back.
I'm ready to hear about the name.
Oh, never
mind.
It doesn't matter.
Throw it bounce, that's not my fault.
That is your fault.
Nothing can be done.
How did that do for Eli?
Nothing I can do.
You aren't like Steph Curry.
Nothing that you just lefty. What? I got lefty. Like that's just a lefty. Well, I didn't even know it was lefty.
All right, so in conclusion, if we kind of wrap up the findings, I've been tallying up on that back board there what the different values are for the slope. In first period, they were all 9.8 or 9.9 something. In your group, they were all 9.8 or 9.7 something. So we're getting really consistent results that reflect something really close to the 9.8 that we would expect for the acceleration due to gravity. Now, I'd like to just comment that often, and this is just, it's intentional on my part, but it's also subtle because we're just getting to the point of the year where I want to emphasize it. But throughout the year, I'd often say when we talked about G, it's the acceleration due to gravity because of the Earth's gravitational field. And so you've heard that terminology, but we've never really defined it. And that's something that I want to talk about today is that letter G, we've used it to find the weight force due to gravity, due to the Earth's gravitational field. We've talked about it being the acceleration due to gravity because of the Earth's gravitational field. But today I want to talk to you about the fact that when you see that letter G, it can mean either acceleration due to gravity or the value for a gravitational field. It is the value of the gravitational field on Earth. And worksheet 3, you're going to be trying to figure out what might that gravitational field look like on other places, other planets, and the moon. Now, in terms of the interpretation of your graph, everyone was able to pretty clearly come up with the slope representing something to do with lowercase g, right? That gravitational field or acceleration due to gravity. And everybody was pretty clear that the intercept should be 0. When there's 0 mass, then we should expect there to be 0 weight, since weight is how gravity impacts mass. Now, the area under the curve, I liked that I saw equations, I saw units, I saw a variety of different units. That's what you should be doing in terms of analyzing it. And again, a reminder, on the rubric, I forgot to type in before I'd already printed it out that I do want you to mention about the area under the curve. So make a little note to yourself, just like you did in the presentation today, talk about what you think about the area under the curve. I do want you to just, a sentence is all, doesn't have to be anything major. Say something about the area under the curve in your report. So don't forget to do that. If you find or look at the rubric on the Axis page, it has it in there, but I'd already printed it and then I realized I forgot to type that in and didn't want to go back and print 70 more pages of it. So I'm just telling you verbally, but it is corrected online. So don't forget to address that. Now, newtons times kilograms. So far, everyone here, I saw several of you looking up, trying to find out, does that mean anything? And no one was able to find anything because it really doesn't have any important meaning. Now we're going to see some other ones as we go through the semester that will, though. And so that's what I'm kind of laying the standard out. Think about the units, think about the equation, do a little research, check with Siri, check with Google, something like that, and try to figure out, if you don't already know, what might this mean? Because sometimes it doesn't have any really valid meaning, but other times it will. And so I want you to have that in the back of your mind that you're always taking those steps. What would the units be? What would the equation be? And then doing a little research if it's not something you're familiar with. All right, so any questions about the mass versus weight mini lab experiment or the reports that are due, not next class, but the class after that, for you guys Friday? All right. So now let's talk just a little bit more about this lowercase g, this letter that we've been using, this variable we've been using both numerically and to calculate the weight of objects. We've used it in kinematics as an acceleration. And what I want to emphasize today is that this value can tell us a couple of different things. And while they're both the same in one regard, they kind of tell us something different depending on our context. So from the lab, if you just strictly looked at the units for your y and x axes, it makes sense, and a lot of you wrote it this way, that the units would be newtons per kilogram. And on, I forget if it was on positive physics or one of the worksheets that I gave you at some point first semester, that even popped up. I remember some students saying, why did they use newtons per kilogram? And that's because this is how we would experimentally determine the value. Just like you did, that's how you can find the value for G in any location. But newtons per kilogram, and a couple of groups even mentioned this, does simplify down to meters per second squared. So it makes sense that it is an acceleration. And because first semester we spent an awful lot of time on kinematics, which involve acceleration, it made most sense to tie it in there for connecting the dots and sort of bringing some things together. But I want you to recognize that lowercase g represents both of those things. And they are the same value on Earth, but they mean something slightly different depending on our context. It is the acceleration due to gravity in meters per second squared, but it is also the magnitude of the gravitational field the Earth generates. So anything that has mass will distort the space around it because of its mass. It's part of Einstein's explanation of how gravity works. And we're not really going to dig into that, but just in case some of you heard that, and if you take AP Physics 2 or college level physics in the future, you'll come back to that concept at some point, that mass distorts the space around it, and that distortion is what we call a gravitational field, right? The value of the gravitational field on Earth is 9.8 newtons per kilogram. And I was going to check on here. I don't remember how they label it here. If they... Okay, yeah, here on the College Board handout, they do refer to it as acceleration due to gravity. But you can also refer to it as gravitational field. And so on the worksheet that you're doing, worksheet 3, when it asks about gravitational field, that's just G. Okay, so I'm going to help you process the first question, and so that if you're not sure exactly how to think it through, you'll have a couple strategies for doing that. So any questions about this sort of synopsis, this quick overview of G, how we've looked at it before and how we're now kind of switching gears and looking at it in a slightly different viewpoint, but still the same thing, just a different perspective on what it can tell us. Yeah, Charlie?
How's that different from like the capital G and then like the constant one?
Say that again?
Like the constant G.
Oh, capital G?
Yeah, I'm still kind of confused like what that is, I guess.
So this is not truly a constant. It's constant near the Earth's surface because the distance, the radius of the Earth is so massive, if I climb up a 10-foot ladder, I'm virtually no farther from the center than I was before, right? Because the Earth is just so massive. So the radius of the Earth is basically how far our centers are apart from each other. So 9.8 in this context for acceleration or the gravitational field is just the relative value for Earth anywhere near the Earth's surface. The capital G is mathematically and experimentally determined constant, regardless of whether you're talking about the Earth or the Moon or Jupiter or Saturn. It was found using not the Earth and the Moon, but actually using massive metal spheres. And so, but then it was found with different shapes and different objects, and then it was calculated based on what we know about the Earth and the Moon, and that it just kept coming back to the same number. So for those of you that have had chemistry, it's a bit like Avogadro's number. It just kept coming up and up and up as they analyzed, well, how many particles are in this number of grams? If you have 12 grams of carbon, it always seems to be this same number. And if you have 16 grams of oxygen, it's always this same number. And it turned out to be what we call Avogadro's number. And so it's the same idea that it is a constant regardless of what matter you're talking about. Whereas this is dependent on where you are. On Earth, it's this, but somewhere else it would be different.
Which is still a function of the other number.
Correct.
So where you are. Okay.
Correct. Yeah. All right. So looking at the first question on worksheet 3, it says the mass of Earth is 81.4 times the mass of the Moon, and the radius of the Earth is 3.67 times the radius of the Moon. If a person weighs 907 newtons on Earth, A, what's the person's mass on the Earth? B, what's the person's mass on the Moon? And C, what is the person's weight on the Moon? So can someone help us out? How would we find the mass of this person on the Earth, or A? Yeah, we know this equation, Fg equals mg, right? And Fg is just the weight. It's the force generated by the Earth's gravitational field on the mass of the object. And so they give us that, 907 newtons. And we know because we're talking about Earth, G's value is approximately 9.8. And you can use meters per second squared, or you can use newtons per kilogram now that you've kind of seen both units and how they fit together. Either way is fine. On the handout College Board gives you, they use meters per second squared. And so the mass is, if I remember correctly, it's like 92.5. If I do that one?
Yeah.
So that's how you solve part A. That's review from last semester, but picking through a newly worded question, not something like the way it was worded before, but basically a review of what you learned last semester. How do we find mass versus weight? And now we've done an experiment to kind of hammer that point home even further. How about part B? What is the person's mass on the moon? It'd be the same because mass does not change because gravity does. Mass is the amount of matter present regardless of the surroundings. So if the mass on Earth is 92.5 kilograms, the mass on the moon is also 92.5 kilograms. However, would the person's weight still be 907 on the moon?
No.
No. So here's what I want you to process. I'm going to show you two ways to solve this. The first one being just straight up proportional reasoning, which is my recommendation. And then the second way is to think through two equations that are on the College Board handout that you can put together and solve for G in a different way. So first, proportional reasoning. If we've got the Earth and we've got the moon, we know the Earth is larger both in radius and in mass, right? And so if we think about the Earth having more mass, does that mean, based on what we know about mass and how mass affects gravity, right? We've got, if I go back to this previous slide, we've got this equation and we know how mass affects the force of gravity, right? Gravitational force. If the moon has less mass, will that make gravitational force bigger or smaller? Smaller, okay? So what I'm going to show you proportional reasoning wise is, let's find the value for G on the moon, okay? And we know what it is on Earth, so let's use proportional reasoning. If I take G on the Earth, and I'm trying to use proportional reasoning, the moon is smaller in mass, so it's going to have a weaker value for G by the mass, right? We follow that? Less mass, less gravitational force. So the amount that it's less is 81.4 times less. The moon is 81.4 times smaller in mass. So should I multiply Earth's value for G by that or divide it? Divide it, because moon's value should be smaller. Smaller mass means smaller G, right? So proportional reasoning, I don't want to multiply it by 81.4. That would make the G value larger, right? I want to divide it by that to make it smaller. Any questions about that first step of kind of proportional reasoning? The moon has less mass, so therefore it's going to have a smaller G. It's 81.4 times less mass, so I should be dividing by that to make the number smaller.
Yeah, you're just plugging in like 1/81.4 into the M.
Yeah, I was actually going to put something else in the numerator, but you could do that and then just do a separate fraction as the radius value. I'm just going to do the radius value with it. But actually, I kind of like that. Let's go with that. So if we just say, if the Earth is 1, then the moon is 81.4 times smaller than that. And so we need to divide by that to get a smaller value of G. Now the moon's radius is also smaller. So if you're on the moon, you would be closer to the moon's center. Would that make gravity stronger or weaker? Stronger. In a linear way?
No, much better.
Yeah, based on this equation, the distance is a quadratic relationship, right? So because the moon has a smaller radius, it should make the gravity bigger due to the radius in a quadratic fashion. So would I divide by it? No, that would make it smaller yet. It should make it bigger by that, right? So instead of dividing, if I say, well, the moon is this, sorry, the Earth is this, the moon is 3.67, but I need to square it because it's not a linear relationship. It's a quadratic relationship based on what we know from that equation. So if I take G on the Earth, 9.8, and divide it by 81.4, because the moon is much less massive, and then multiply it by 3.67, because it has a lower radius, which would actually strengthen the gravity, right? So one factor, the mass, is weakening the gravity, but one factor, the radius, is actually strengthening it. You follow okay on that?
Yeah.
So if I take that, what do I get if I go ahead and plug in 9.8, divide it by 81.4, and so if we say G of the moon would be equal to 9.8 times those two proportional ratios. So what does the G for the moon end up being?
Something around 9.
Yeah,
1.6.
1.6. I think I got like 1.62 or something like that, but you just take 9.8 divided by 81.4 and then multiplied by 3.67 squared. So then how do I find the weight on the moon?
Multiply. I mean, yeah, multiply mass by that.
92.5 kilograms, because that's not going to be different. Times 1.62 meters per second squared. And the answer's on the back of the sheet. I forget what it is, but 500 or something like that.
150.
Or yeah, 150, 500. All right, now, before you go, I want to show you real quickly in about 1 minute another approach that some students feel better about or more comfortable with. We've got two equations, right? We've got this FG equals MG, but we've also got now, after our class a couple days ago, FG is GMM over R squared. So another option would be to say mg, the mass of, let's say, a person, times the acceleration due to the force field of the planet, the gravitational field of the planet, would equal that constant g times the mass of the person times the mass of the planet. We'll just say Earth, if we're talking about Earth, but it could be any planet, right? Over the distance. Now that's supposed to be the distance between their centers. But if I know the radius of the Earth, does it really matter how big I am? The Earth is so huge, if I add on a couple extra feet, it's not going to make a difference, right? Even on the moon's not as big as the Earth, but it's still so much bigger than me. The radius of the moon added on a couple more feet, it's not going to make a difference. So this is basically just going to be the radius of whatever the planet is when we're talking about planets and moons and huge objects like that. If I solve for G, you notice how the mass of the person cancels? So the way you can find G is to take little g, the way you can find G, the gravitational field, is to take capital G, the constant, times the mass of the planet, divided by the radius of the planet, squared. Now the downside is you need to know the mass of the planet or some proportion like that we had up there, or you need to know the radius of the planet or some proportion. And so this is just one more way you could solve for lowercase g, and you could work out these problems. All right, that's all we have time for today. Do your best on trying to wrap up the rest of the questions on that worksheet, and I'll see you Wednesday.